they sort of, if I believe the model, at least the model was going to predict that one of these three is the best thing to do. But you can't figure it out until you punch in the numbers. And so you punch in 28,000 times an A, increase average teacher salary. So average teacher salary, you multiply 28,000 times 0.00062. And then you multiply 30,000 times 0.00062. That's the mechanics of how you would do that. Do you understand that? 28,000 times 0.00062, 30,000 times 0.00062. And the numbers come out to be 17.36 and then up to 18.6. Which means a 1.24% increase in students passing the exam. The numbers go from, once you plug in the two numbers, 28,000, 30,000, you get 17.36 and 18.6 is the two numbers there, which is a 1.24% increase. The next one, reduce student-teacher ratio from 20 to 819. You go to the student-teacher ratio column. See, it says minus 0.47 there. You multiply that by 20 and that by 19.
Does the negative make a difference in your calculation?
Yeah, well, it's actually the percent. Because you're going from 20 to 19, so the percent passing the exam will go up. But the two numbers you get are you get minus 0.954 with the 20. You see, it's going up. The idea is with student-teacher ratio is that rather than sort of a student-teacher ratio goes up, you do better. The concept is that people think that smaller class size is better. So it's an inverse relationship. So the concept is that 19 is better than 20 in this case. So that's why with the 20 you get a minus 9.5, and then with the 19 you get a minus 9.063, or you get a 0.47% more passing the exam. And the last one, eliminate uncertified teachers, from going from 4% to 0%. So from 4 to 0%, you go to sort of uncertified teachers, percent uncertified. And first you multiply 4 times minus 0.16, or it would be about 4 times 16, or whatever, 64. Or 0.64, rather. 0.16 times 4 is 0.64. You put a 0 in there, you've got 0 times that number, that's just 0. So you've dropped from 0.64 to 0, or in this case, 0.649% more passing the exam. So, based on this study across school districts, the biggest effect is increasing the salary. Those places that had higher salary had a 1.24% increase, reduced the student-teacher ratio, but had a 0.47% more passing, and eliminating all uncertified teachers had a and this was a revenue neutral. This was spending the same amount of money. Now, why would you not have complete confidence in sort of that actually being the best solution? Because maybe there's other variables that belong in this model that essentially the school districts that have higher salary, even though we appear to have control for some socioeconomic things here and such, maybe there's something else going on that's not in the model that leads to the higher teacher income school districts doing better on the exam. That's the pause you have. Otherwise, but that's not the question. That's the pause you'd have in sort of being completely confident. If you really like this model and think it sort of includes almost everything that's relevant, then you go, I'm sure. I'm sure the best thing to do is raise the salaries and the district's not doing as well, and we'll get the most effect, the greatest effect. So for like a regression question on an exam, part of it would be sort of maybe asking you sort of to calculate it, picking the best one, and then I didn't in this case, but might also sort of ask you some question about sort of why you might not have complete confidence in that actually being the best one. And if you say I do have complete confidence, you would say, because I think this is a really good model, and it has all the really important variables in it.
And if you had all the important variables, would your R squared be 1 or close to it? Or if it was close to it, could you say then that that model is like? all the- all the
I'm not gonna do one, but yeah, certainly is the R-squared sort of, and sometimes things like understand that across individuals, you're never getting sort of R-squared, sort of much above 0.5 or 0.6 most of the time, and sometimes, but yeah, something like across school districts, across states, across countries, you can get some, yeah. Now, except, yeah, you have sort of generally more confidence in the effect with one cause. Generally, that's a good thing to sort of say. That's one way to show it. Say, oh, the R-squared is 0.9, so this is a good model. And so I'm confident in this effect. The only pause is still, is one of those variables in the model actually a confounding variable for something else? Like I don't know the teacher salary necessarily is, but is something in the model a confounding variable for something else? Like an example for economics of books and books in the house sort of. Books in the house seem to really help to predict